Okay, so this is a short lecture. We will see a short video on amplifiers, right? So we have been seeing some of the snippet of these amplifiers and how to basically get amplification from MOSFET. So we have seen some of that in small signal. And after now understanding that to one thing which central concept which we understood that if we want the MOSFETs NMOS or PMOS to behave or to do the amplification action, we need to bias them to a DC voltage, right? So there is a bias voltage which is needed. And on top of that, then we are going to ride our small signal which we are acquiring from a physical system like microphone or so, right? And then that is coupled to your DC which you are providing. And then we expect this signal to be amplified, right? So let's say if there is an input signal which is coming in from here, which we call, let's say, for example, V small v in, right? And we expect an output which is small v out. And this V in by V out, oh, sorry, V out by V in is something which we know as the voltage gain of this MOSFET or this amplifier circuit. So we have seen the biasing circuits in the previous discussion of on current mirrors. We have seen how do we generate these biasing voltage using a golden current source, which we have obtaining from somewhere. And now the question which we are delve into that what are the different when we are designing this amplifier, is the gain only thing or do we need to worry about other things when we are designing these amplifiers, right? And we have briefly seen some of the circuits, so I'll go over them again. So one thing which we see that if we were to we want this amplification to be there, one of the key thing which you would see is that this quantity needs to be constant, right? Constant means that when we see you would see a characteristic like this, right? Which means that it is a linear characteristic. So V out versus V in would be a linear characteristic. That is one of the key of amplifier, that I want V out versus V in to be linear. Uh, and that is when you say, okay, this is a, and obviously, needless to say, this slope needs to be more than one, so that's when we would say this is amplification. Otherwise, if it is not less than one, that means you see that the signal had deteriorated, right? So that means there's a lot of attenuation in the signal which you have introduced. So now, after the linear understanding that we want this to be linear, this V out by V in, which is all small signal, um, one can talk about that. What is that V out by V in? How do we obtain this? So for a basic MOSFET circuit, if you remember like this, what could be the ideal load which we can consider here? So if you remember, what would be the load which would give you the intrinsic gain? So if you remember, we consider a load of a current source, right? This would give you, and if you were to recalculate for this circuit, your gain would come out to be minus GM RO. And this is the intrinsic gain of MOSFET, right? When we are having current source as a load. Now, the question is this the only metric when we are designing these amplifier? And the answer is no. When we are designing any analog circuit, such as amplifier, there are multiple things which we have to take care of. It's not just that you design it only for gain, and we will be also saying that from an example. But let me just first go over that what are the different quantities which one needs to look at, right, when they are designing. So gain is obviously, we have been talking about gain, but that is not the only thing. Another thing which we talked about briefly in this metric or in this particular video is the linearity, right, which is very important. And we have briefly talked about this before also, and we saw that when there is no linearity, this can result in harmonics, like there are higher frequency components available in your output which is not needed, which are unintentional or undesirable, right? Other than linearity, what else comes into play, right? So this is again, there are multiple things, and we would have probably seen this also, that when we were talking about, I think in the case of current mirrors, we have seen this mostly. What is the output resistance, right? Because this is very important, and we will see why it is important. But let me first write input output impedances. First, let me write all the figure of merits which we talk about, and I think you can find it in the book textbook of Rajavi also in the chapter 3, right? And you can see the supply voltage being 1. Then there is voltage swing. Then there is speed, input output impedances, your power dissipation, and noise, right? So these are 8 things you have seen: 1, 2, 3, 4, 5, 6, 7, 8. Gain we have seen, linearity we have seen, supply voltage you understand, and maybe not, but the supply voltage is directly related. So if we talk about this particular component, the power dissipation, it would depend on both supply voltage and also the current which you are using in your circuit, the bias current which you're passing, right? So that is what you are drawing from the supply. But is that the only thing the supply voltage affects? No. Supply voltage also has an impact on the voltage swing. Now let's understand what is voltage swing. I think you have briefly seen this also in the input output curves, right? When we were drawing these input output curves of inverters, we saw that. So when we bias something here, you see in the linear region, what are the maximum and minimum voltage which you will have, right? So this is, let's say, Vmax, and this is what Vmax. So you see that the minimum and maximum you can have is between 0 and VDD, but not necessarily, right? Because we discussed that if we switch just the position of the NMOS and PMOS and CMOS inverter, these numbers, whatever you get as a swing, would change, right? Because of the drop which happens, the VTH drop. So that means this is a very important metric which is decided by VDD. If VDD is very small, obviously your swing is going to be smaller, right? So this is a very important metric because that defines that if I'm able to find the linear region, right? I'm passing a signal here. If the swing is much lesser, then what happens is that my signal, output signal, basically gets cut off, right? So though I'm expecting a signal to be like this, but if the swing is not enough, so this swing, if it is like this, then you see that the signal is cut off because of the swing. So this is important, right? Speed. Yes, speed is also important, and one case which we have already seen, probably you may relate the speed to the frequency, right? The higher frequency we are working at, higher speed is your amplifier, and because it's directly related with the gain, and we have seen the frequency which defines the bandwidth, and typically if the response is like this, we see this is what means by the bandwidth, right? So the gain and speed or the bandwidth, they are very much related. The voltage swing we have seen, this is related. Voltage swing, supply voltage also affects power supply. Now gain, does it also impact input and output resistance? First, let's see why it is important to have input output impedance. Why do you think that we need? So let's say this is an amplifier. There is an input resistance we are saying, and there is an output resistance, right, which you are having. Why is it important, this input output resistance, for this amplifier? Because this, you are going to connect this amplifier to certain load and certain source, right? So there is a source which you would be connecting this to, right? It is not a standalone. It is going to take some source, and it is also going to have some load which it would drive. And typically the source resistance we can model, if in voltage model, we can model with the source resistance like this, which is a Vs. And the load we can model, let's say, with simple resistive load, for example, here, RL, right? Which is your V out. And this is your V in dash, and this is your V out dash, right? Which is coming from amplifier. So we know the relation between V out dash and V in dash, which is just AV times V in dash, if we assume it is a linear thing. Now, V in dash, if it was described in terms of Vs, this would be Rn divided by Rn plus Rs. That would give you Vs, or let's call it V in, actual V in. Right. You understand, right? So this V in is the actual source, but it is passed to the amplifier because there is a source resistance which is coming. Let's say in microphone, you will have a resistive load, resistive source, and then you're passing it to the amplifier, right? So that means you see that there is a certain voltage drop which could have happened because of the source resistance. And same thing for V out. We see that there is a relation between V out and um, so V out is basically what is passing through RL divided by RL plus R, which is your V out dash. So then if we were to write V out and V in, we can see that V out, VO is nothing, is just AV times these two multiplication, which we see. So now what we see, we earlier assumed that V out and V in would be just equal to AV. We see that because of the source and load, this is not the picture, because we need to take into account these, whatever the drop or the ratio which is coming because in this voltages, because this is transferring from source to the input of the amplifier, there is a particular certain drop I may expect. And when does this drop become prominent? So ideally, what do we want? We want these two values, let's call it, which is at the source side, right? Source ratio. And this is the load ratio, LR. So we want both SR and LR ideally to be 1, right? Because we don't want our gain to suffer. But what might happen, we see when your Rn, if it is nearly same as Rs, right? Because, so, okay, so first let's see when do we achieve this to be 1. So when do we achieve it to be 1? When obviously your Rn is much higher than your Rs, right? Then you see clearly this SR becomes 1. Similarly, in this case, when your R out becomes much smaller than your RL. then your LR becomes 1. So then this poses a very important condition on our voltage amplifier, because we are using this is your voltage amplifier, which we have been talking about. This poses a very important condition that your R in should be very, very high, while your R out should be very, very small, right? So this is ideally, we say ideally, this is tending to infinity and this is tending to 0, right? So now, is that the case? No, maybe not. If you have badly designed the amplifier, if you have not taken, you have only worried about gain, 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 and you have not taken into account this important aspect, then obviously you would have a big problem with your gain, the overall gain of the amplifier. That means when you're passing from source to the load, you will see your signal is lost because you didn't do a proper job of RN, RN and R out. So that is the significance of why one needs to look at the impedances, and we'll see this is very much related to the gain of the amplifier, right? And why? Because we clearly see, if you were to see, that the R out, which is the RDS resistance, is coming into the gain, and it would also be seen at the in the output impedance, right? So that is becomes very, very important. Now, what else is left? Yeah, noise. So noise, you see, noise is something which we will also talk about, and we have briefly talked about in the case of a differential amplifier. We talked about that when we use a differential stage, for example, like in op amp, this can really help us minimize the noise, which we, or the noise cancellation. So noise is a reality in all the analog circuits, and this would be always there, and we'll briefly talk about noise in the later part of the course. But we see that it is something to be dealt with when, or kept in mind when you are designing this analog. And one way to really counter noise is something where differential, other than the differential we saw in the amplifier, that when you keep the voltage strength of your signals quite high, that means that they would be much higher than the noise floor which you have, because noise is small. But if you supply voltage in a signal, let's say become, so it is very much related to your voltage swing, right? So because if your voltage swing is very, very small, that means noise can kill your signal quite a bit. So that is why the voltage swing has to be something appreciable. So that is about the different trade-offs one would have in the case of when they are designing any analog circuits. Particularly, let's say in this case, we are going to look at amplifiers, right? Just to give you a snippet to think from, that what would be the problem when we design such a circuit. So for example, if you know that we have talked about quite a bit, that how do I increase the R out or the gain of the circuit? So one of the stage, I think I would just give you this problem, and you can have a look at this problem. So this is where you are applying V in. Others are your biases. So this is your VB1, let's say. This is where you take the output, V out, and the PMOS stage also, which you apply, are going to be, let's take this also to be, so this is your VDD, and this is your, okay. And you see what is the good part with this circuit compared to obviously the one which we have drawn here. So let's say this is circuit 1, and this is circuit 2. So compare circuit 1 and 2 on the matrix which we have talked about. Okay. So you think about it, that what would be better, what would be worse, that kind of thing. you have to just talk about. And the very simple hint is that you draw the small signal circuit, try to find the gain, try to find the input output impedance if you can, right? Speed we have not about talked about, so you cannot find. Power dissipation you may assume to be same. Voltage swing definitely you have to see also. And yeah, supply voltage same for both, right? So that is how you think about it. Okay,